Solutions. This is a very vocabulary intense topic, but it is very essential to the rest of your understanding of chemistry because a lot of the stuff that we do is in solution form. So let's get started with some of those words. We'll first talk about the different types of mixtures. And we talked about this at the very, very beginning of chemistry, but we'll talk about it here because it does play a role. So our types of mixtures, and mixtures are things that are not chemically bonded to each other. So you can have a heterogeneous mixture, which has non-uniform mixture composition. They're going to look different, and you can go from the root word hetero, different. So you would be able to pick out the different pieces of the mixture. A pizza is a heterogeneous mixture. You can see all the different pieces, and if you don't like one of the toppings, you can take it off. Or if I have a mixture of black pebbles and white pebbles, you could pick out all the white pebbles if I asked you to. A homogeneous mixture has uniform mixture composition, so it's going to look the same, and that's what homo means, same. So this would be an example of sugar water. You wouldn't know by looking at it that it is a mixture of sugar and water until you went to take a sip of it, and it would not taste like water. It would be a lot sweeter. Now we have different types of mixtures, and they are differentiated by the particle size. So first we're going to start with suspensions. Suspensions are heterogeneous mixtures of two or more substances where large particles settle out unless stirred. So the classic example of a suspension is muddy pond water. And we'll get to that here in just a second. The reason these particles settle out is that they have a really large size. They're over 1,000 nanometers in size, and the solute just can't support that much or that size of particle, and so they end up falling out eventually. And again, the example is muddy pond water. I like to think of chocolate milk. So if I were to have chocolate milk and I use the syrup chocolate and I put it in the milk and then I stir and stir and stir and stir and stir and stir and stir, no matter how much I really stirred, by the time I get to the bottom of the glass, there's still some chocolate in the bottom there. And that's because the particle size is just too big, and so it eventually will settle out. The same with muddy pond water. If you have a cup of this muddy pond water and set it on the table, over a day or so, the mud would fall to the bottom, leaving the top relatively clear. Another type of mixture is called a colloid. You've actually experienced quite a few colloids in your life, but you've never been taught that term, or I suspect you haven't. A colloid is a heterogeneous mixture of intermediate-sized particles that are small enough to maintain a homogeneous appearance, but are large enough to scatter light and do not dissolve. All right, so again, a heterogeneous mixture, you can kind of see the different parts, but you have to have a little bit of help with this one. And they are of intermediate size, so they don't settle. They will stay in solution forever, but it is still a heterogeneous mixture. They scatter light. The particle size is between 1 nanometer and 1,000 nanometers. We talked about nanometers. That's 1 times 10 to the negative 9 meters. So a decimal point, 8 zeros, and then a 1 meters. So they're still really tiny, but they're small enough to stay in solution and not settle out. Mayonnaise is a colloidal dispersion of water droplets or oil droplets in water. I always say if you like mayonnaise, never, ever, ever read the label. Another example would be fog. When you're driving through fog, you're driving through a colloid. And you know this because it does exhibit the Tyndall effect. Fog does. When you're driving through fog, you're supposed to have your headlights on the lowest setting, because if you were to turn them to your bright lights, then what's going to happen is basically all you can see is a wall of white. The light leaves your headlights, hits all of those little particles, and it scatters the light back at you, and so all you see is white light. The low lights, not as much light is being given off from your headlights, so not as much is being scattered back to you, and so you can still see the road. So that's the Tyndall effect. And again, it occurs when light is scattered by colloidal particles dispersed in a transparent medium. different types of colloids. We have emulsions, which they a lot of times use for medicines. I had a veterinarian come in and talk to one of my chemistry classes, and he specialized in pet medicine. One of the things about giving medicine to pets is if it doesn't taste good, they are not going to eat it. And if you've ever tried to get a cat to take medicine that doesn't taste good, you were met with fierce resistance. So a lot of times what he would do is take the medicine and emulsify it with like a ointment or something like that. And then you could just put the ointment on the cat's inside of their ears where the blood vessels are really, really close to the surface, and the medicine would get in their bloodstream that way instead of trying to get them to ingest it. Smoke is a colloid, foam, milk, aerosols, like I said, fog, gels like Jell-O is a colloid, and clouds. Here's an example of that Tyndall effect. The solution on the right is a solution, and we'll talk about those here in just a second. The particles are really, really tiny, and so the light just kind of passes through. You can just see the beam of light very, very small. The one on the left is a colloid. You can see that beam of light is much more scattered, and that is because those particles in there are large enough to scatter that light. Our last one is a solution. Now, a solution is the only mixture that is homogeneous. So if it's a homogeneous mixture, it's called a solution. So it's a homogeneous mixture of two or more substances in a single phase. So they're both liquids, they're both gases, something like that. The particle size is really, really tiny. It has less than 1 nanometer in particle size. So really small. They don't settle out, and they don't really scatter the light. Materials must be soluble to form solutions. So here's another term that we need to know, and a lot of times they do sound a lot alike: solution, soluble. Soluble just means capable of being dissolved. So we know that sugar will dissolve in water. So sugar is soluble in water. But there are other substances that are not soluble in water. Calcium carbonate is not soluble in water. Oil is not soluble in water. So we'll talk about the reasons chemically wise that is the case, but we need to know the term soluble. And this is an example of sugar cubes. Sugar cubes are soluble in water. Eventually all the sugar molecules become uniformly distributed among the water molecules. Now, a solution always has two parts, and we need to be able to tell the two parts apart. The first part is the solvent. Solvent is the substance doing the dissolving. Water is a very popular solvent. It dissolves a lot of different things. Alcohols are also solvents. They will dissolve things. Solute is the substance being dissolved. Now, we're going to get into some math later on in this chapter that does require us to know the difference between a solute and a solvent. And you will have to get those clues from the context of the problem. Solute will be the substance dissolved. So it might say that you have calcium chloride is dissolved in water. Well, calcium chloride is the solute, and water is the solvent in that situation. Or one that you may be more familiar with, sugar in sugar water. Sugar is the solute. It is the substance being dissolved, and water is doing the dissolving, so it is the solvent. Solvents dissolve solutes. Types of solutions. We can have all kinds of different ones. I've just talked about solid liquid ones so far, but there are different types. Gas-gas solutions. That's like the air around you right now. It's a mixture of gases. Gas-liquid solution. That would be like a soda where you have the carbon dioxide dissolved in that liquid. A gas-solid solution. This may be something like a marshmallow where you've got the gas dissolved in that solid. Liquid-liquid, that would be like alcohol and mixed with water. Liquid-solid, that's sugar dissolved in water. And solid-solid solutions are what we call alloys. So a solid solution of two or more metals that are uniformly mixed. An example would be brass. Brass is a solution of zinc and copper. Bronze is, I believe, tin and copper. 14 karat gold jewelry is also an alloy. Jewelry is really just too soft to be, or 24 karat gold is really just too soft to be used in everyday jewelry wear. If you have some heirloom pieces, there's things that you only wear that are 24 karat gold. Those are things that you only wear on special occasions. But for something that you're going to wear every day, if it's 24 karat gold, it's really not going to stand up very well. 24 karat gold is soft. Pressing your fingernail against it would make it dent. It would bend and scratch very, very easily. So what we do is we alloy it with silver. It gets the strength and hardness of the silver while still maintaining the look of gold. So that's what 14 karat gold jewelry is. And there are all kinds of different types of gold. So usually they have gold mixed with silver and or copper. If you have yellow gold, and that's pretty common around here, most of the gold that you'll see sold in the States is yellow gold, and it has a bit of copper and silver mixed in there, more gold, silver. White gold is nickel, zinc, and copper mixed with that gold. Rose gold, now this is often called Russian gold, is really copper mixed with gold, and it's called Russian gold because that's the type of gold they have. They have a lot more copper in the rocks there in Russia, so most of the gold mined from that region is rose gold or red gold. There's also green gold, which has silver, zinc, and copper mixed in there, and so you can kind of see with this triangular graph on the different mixtures of copper, silver, and gold that we have. Other alloys, you've got woods metal. Probably not too familiar with that unless you work with or have worked as an auto mechanic or know a lot about cars and things like that. But it is used in those situations for fuse plugs and automatic sprinklers. So it is an alloy of bismuth, lead, tin, and cadmium, and has that low melting point, which is what you want for those types of uses. Yellow brass is copper and zinc, like I said before. Stainless steel has its iron, and it's mixed with carbon and chromium and nickel. And it's really that chromium that's there on the surface that resists corrosion and makes that steel stainless. So used in tableware, like your forks and knives and stuff like that. Plumber's solder is lead and tin mixture, and so that's soldering joints, putting two electrical wires together. And we have sterling silver, which is silver and a little bit of copper, gives that bright surface, which is used in service tableware. This last one is interesting, probably to older generations more than you guys, but dental emeline. What you have there is these are your fillings. These are the silver fillings that probably your parents have. They have silver, tin, copper, and 2% mercury. Now that mercury, we've learned, mercury vapor is very dangerous. It does cause you to go crazy slowly over time, and we have found that these fillings do leak mercury over time, and they're in your head, so you are breathing them. That's kind of why we've gone away with them, from them. The reason we used them in the first place is because they would kind of mimic the same sort of thermal expansion that your tooth does. So if you drink something hot, your tooth kind of expands a little bit. And you want the filling to expand a little bit as well. And the mercury helped it do that, but it also had some health consequences. So now mostly what you have is some kind of composite where they have to expose it to UV light to get it to harden. All right. Now, let's talk about solutes. These are the things that are being dissolved. Solutes can be electrolytes or non-electrolytes. Do you remember what an electrolyte is? It's something that can conduct electricity. And the reason it can conduct electricity is because it has ions. And those charged pieces are able to move from one place to another. So salt was our example of an electrolyte. When you put salt in water, it splits into its ions, and those ions are available to carry an electrical current. Sugar is a non-electrolyte. Sugar is a molecule. It's not made of ions, so there are no charged pieces to carry the electrical current. Solutes of ionic compounds and certain highly polar molecules are electrolytes. Water is a solvent, and it's a non-electrolyte. Only solutions of electrolytes conduct electricity. So if that's true, why do we worry about putting a hairdryer in the bathtub? It's not because of the water as much as it is the other stuff in the water that will conduct electricity. The solution process. So here we're going to get a nice visual. So if you're a visual learner, this is the part you really want to listen to. Water is a polar molecule, which means it has those partial charges, and it also has hydrogen bonding, holding those molecules together. So here we have a nice model of a water molecule. You have your red oxygen and then the two purple hydrogens there. And because oxygen is more electronegative, the electrons spend more time with that oxygen than they do with the hydrogen, leaving these slight charges. So oxygen develops that slight negative charge. Write it a little bit bigger there. And each hydrogen develops that slight positive charge. Now this is going to give water a lot of its special properties that we'll need to discuss in this chapter. This is a symbol of some hydrogen bonding. Because we have an electron deficient hydrogen right here, because the oxygen's pulling on its electrons, it sees this unshared pair on a neighboring water molecule and becomes attracted to it. And so we have those hydrogen bonds. Remember, those are just forces of attraction, not actually bonds, but they're just really strong forces of attraction. All right. Water molecules surround ions of other polar molecules one at a time, forming hydration shells to make a substance dissolve. So this is what is happening when you dissolve salt or sugar in water. Let's talk about salt in water. So we have our water molecule, that's polar, and here we have our salt molecule. Now, sodium is going to be our positive ion, and it is the purple one. Chlorine is our negative ion, and that is the green one. As the solution happens, water molecules, because remember this oxygen has that slight negative charge, and each of the hydrogens have that slight positive charge. The sodium is positive, and so those negative oxygens, notice that the red is lined up with every water molecule, is lined up with that sodium ion. So the slight negative of the water molecule becomes attracted to the slight, or the actual full positive of the sodium. And the same thing kind of happens for the chlorine. But notice the water molecules are flipped around now. Because chlorine is negative, those slight positive ends of the hydrogen and the water molecule are attracted to that negative of the chlorine. Because sodium and chlorine are separated, and we have these hydration shells from the water molecules, keeping them separated, that is what causes salt to dissolve in water. I have a few more visuals here to help you along with that. So this process is called hydration or solvation. So you can see another model here. We have our positive and negative ions of some kind of ionic solid. And then we have our water molecules. Again, this is our oxygen right here, and it would be attracted to something that's positive. Here, this negative ion is attracted by the positive or slight positives of the water molecule. And then here you can see the hydration shells where we have those ions separated. I have a little animation that'll help you see this in motion. Just a second. All right, so we're going to put some salt and some water. and stir. And then we're going to get to see what's happening on the inside. So you can see those water molecules becoming attracted to those ions, and they do orient themselves according to the polarity, forming those hydration shells and dissolving that solid. Okay, 3 factors that affect the rate at which a solid solute dissolves in a liquid solvent. So I'm already using the terms here, and I will expect you to know them as well. So we're going to dissolve a solid in a liquid. So for simplicity's sake, we can talk about sugar in water. Or I say, if you know how to make sweet tea, you already know how these 3 factors. So when you're making tea, do you boil the tea or boil the water, make the tea, and then let it cool down before you add the sugar? No. You're actually going to add the sugar while it's still hot. And you know this from if you go to some place and they don't serve sweet tea, so they bring you a sugar packet and then iced tea. It's really hard to get that sugar to dissolve in the iced tea because the tea is cold. So we want that solvent warm. The other thing that you probably already know, when you make sweet tea, do you use sugar crystals or sugar cubes? Well, here we use those sugar crystals. And the reason is because it has an increased surface area. And the last one is when you make tea, you have the tea, dissolve it with the sugar, and to help the dissolving process, you stir. So that is another factor. And those are our 3. I'll go through them again here. So increasing the surface area. If I have a sugar cube, when I put this in water, water can only get to those sugar particles that are on the surface. There are still sugar crystals on the inside of that cube that don't have access to the water, so they won't dissolve. So what we do is we smash it into pieces. And the smaller the pieces, the greater the surface area, because then the water can get to all of those tiny crystals rather than just those at that surface. All right, so the more finely divided a substance, the greater the surface area, the more surface water molecules can access, and the quicker the substance dissolves. So increasing the surface area is a way of affecting the rate at which a solid solute dissolves in a liquid solvent. Another one would be agitating a solution. Agitation is another word for stirring. So more agitation, the more particle movement, and the quicker it dissolves. So we can get the water more access to those solids. And heating a solvent. If we heat a solvent, the greater the particle movement, because as we increase temperature, those particles start to move faster. We also have greater breaking of the intermolecular forces. Water has hydrogen bonding, and it's all attracted to itself, so to get it to dissolve something else, we have to break those hydrogen bonds so that it's attracted to something else. So that heat is also available to break those forces of attraction, and it also increases that solubility. So those are our 3 factors. You will have to know these 3. All right, I think we're going to stop with this video cast, and we'll start with another one on solute-solvent interactions next time.